Okay, so in this video we are going to discuss about variation in power dissipation, variation in power dissipation with the change in resistance and also with the change in angular frequency. Okay, and we will get one angular frequency for which power dissipation is maximum. We call this frequency resonant frequency. Okay, apart from this angular frequency omega naught, we will also find this upper band edge frequency, lower band edge frequency at which power dissipation is half of the maximum. Okay, and what we want, we will also discuss about quality factor which will depends on these two values also. The reason is, what we want resonance. For example, when you are tuning for FM or radio frequency, what happens, at some particular frequency you get the maximum power, you get the maximum current, right? And when you go away from that frequency, what happens, power is dropped, signal is lost. What you want, you want this signal to be very strong at a particular point, that is omega naught. And what you also want, you want this radio signal to disappear, okay, to diminish quickly. So we will find this omega and omega 2 and omega 1 where the power is half of the maximum. And what we want these values, we want these values to be very close to omega naught. That means you change the frequency slightly, and power is dropped quickly. Okay, and this thing we will define one quantity, that is quality factor omega naught by omega 2 minus omega 1. Okay, if this factor is large, if this factor is large, the quality of radio signal is very good. Okay, that means you will get a very high power dissipation at a particular frequency omega naught, and that signal will diminish quickly when you change, when you increase the frequency or decrease the frequency. Okay, so let us discuss these things. First of all, power dissipation. Dissipation, and we are talking about AC circuit. So P average, P average will be RMS value of EMF, RMS value of current, and one more thing is there, we call it cos alpha, that is called power factor. And clearly IRMS, RMS value of the current is related to the ERMS. By this, Z is called total impedance. Okay, total impedance of the circuit, and cos alpha is called the power factor, that is R by Z. So I will write these things here also. Basically, Z is total impedance. Total impedance, and its value will be R square plus omega L minus 1 by omega C, the whole square under root. And cos alpha is called power factor. We also discussed about it, and that is R by Z. So clearly P average will be ERMS the whole square into R by R square plus omega L minus 1 by omega C the whole square. Okay, I am not putting a square root because this is Z square. When you do Z square, you will get this thing without the square root sign. And 8 omega, if not 8, if omega L minus omega C is 0, if omega, or that means omega is 1 by root LC, I will give this frequency, this angular frequency, a name omega naught. At this angular frequency, what will happen? This part will become 0. This part will become 0 and P average will be maximum. If this part is 0, average power will be maximum, and that will be ERMS the whole square by R. So this thing happens at uh, 8 omega naught. I will draw a first a curve, okay, resonance curve. Okay, we will see a resonance curve, then we will find different frequencies at which max average power is half of this value. Okay, from the graph you will get an idea why are we doing it. Okay, from the graph you will get an idea why are we trying to find those two frequencies. So this is omega and this is I, this is current. Okay, and we have seen that we have a value of omega, omega for which power dissipation is maximum, right? And suppose the resistance is, we have some resistance in the circuit. Okay, suppose we have some resistance in the circuit, and power dissipation formula I will write it again. Okay, it will be great. ERMS the whole square by R square plus omega L minus 1 by omega C the whole square into R. I will also write IRMS formula, which will be ERMS by R square plus omega L minus 1 by omega C under root. You can clearly see that 8 omega naught 1 by root LC, both things are maximum, right? So at omega naught, what will happen? Both things are maximum. So current is maximum here. If you decrease the omega, 1 by omega C will be greater than omega L. This will become non-zero. And current will increase. Okay. Also, if you increase omega, this omega L will become larger than 1 by omega C. This is again non-zero, and the current will decrease. So you can see that at omega naught current is maximum. Decreasing or increasing omega gives us a smaller current. Okay, right now I am taking one value of R. Let us say this is what, 1 ohm, and IRMS max, it will be ERMS by R. So clearly if you make the resistance half, suppose that here resistance is half of the original, so what will happen, current will get larger. Okay, current will get larger. So this value of resistance is 0.5 ampere. Now suppose you decrease the R value even further. Okay, so R value is again decreased. I am making it 0.05. So what is happening here, this R is 0.05 ohm. So what is happening here, you can see that when we decrease R, clearly I value is increasing, but this resonance curve is getting sharper. Here it is flatter, here it is less flat. Okay, and here it is even less flat. Okay, if you decrease the R value again, the curve will look like something. Suppose the R value is even less, I will say 0.13 ohm. Okay, so what you see, sharpness of the resonance curve is increasing when we decrease the value of R. What does it mean? We will get a good signal. We will get a good signal at omega naught, and current will decrease quickly. Current will decrease quickly if you decrease the omega or increase the omega. Slight change in frequency. At a particular frequency, we are going to get maximum value of current. If you increase the frequency, current will be reduced sharply. If you decrease the frequency, current will decrease sharply, and that is what we want. Okay, we want a clear signal at a particular frequency. Okay, and then that will define the quality of the signal. So I will talk about this curve. Okay, I will talk about this curve. Okay, and I will call this frequency omega 1 and this larger frequency omega 2, at which power dissipation is half of the maximum. At omega 1 and omega 2, what is happening? Power dissipation is half of the maximum. So let us find omega 1 and omega 2. So P average is half of the P average maximum. Okay, so P average was ERMS the whole square by R square plus omega L minus 1 by omega C the whole square into R. Okay, this was the average value, and this half is the part of the equation, part of the condition. Okay, and this average power was ERMS. This is the maximum average power. Okay, this is the maximum average power. Clearly ERMS part is gone, and what will happen, you will get one side R square plus omega L minus 1 by omega C, and on the other side you will get 2R square, 2R square. This calculation you should do on your own at least once. So you are getting this equation, both are squared. When you take the square root, we are going to get two equations. When you do when you take the square root, you are going to get 1 plus R, and other you are going to get minus R. Okay, what is the meaning of this? What is the meaning of this? This omega is larger than omega naught. So omega L is larger than 1 by omega C, and this value is positive. Now if you decrease the angular frequency, what will happen? Omega L will become smaller than 1 by omega C, and this quantity will become negative. Okay, so we are getting two equations, and you can clearly see that this will turn into a quadratic equation. This will turn into a quadratic equation. So it looks like we are going to get four solutions, but out of the four solutions, two will be discarded. Okay, so let us find first one. I said that here omega will be larger than omega naught, so I will call it omega 2. So omega 2 L minus 1 by omega 2 C is R. Omega 2 LC, this will go this side, and this will become W2CR, and in this side this will be a squared. Okay, W2CR, and this will become minus 1, and this is 0. So omega 2 will be, we are going to use quadratic formula, minus b. Minus b means minus minus CR plus minus under root b square, that is minus CR the whole square minus 4 AC. 4 is 4, A is LC, and C is minus 1. And then we divide by 2A. 2A. A is what? LC. A is, this part is A. Okay. So what you are going to get is omega 2. Now see. Okay, let me write it. Then we will discuss. This will become positive. Okay. This will become positive. Okay, so first of all, we have to remove this minus sign. The reason is that omega should not be negative. So I will remove this minus sign. It will become like this. W2 will become like, if you divide it, C will cancel, R by 12 will be there, and this will be plus. This will again become R by 12, R by 12 the whole square. Okay, you have to do it on your own. Okay, and this will become 4L square C square under root. So I will write 1 by LC. Okay, this is what you are going to get. Okay, we get this thing using the first equation, and one of the value is discarded. Now we will use the second equation. Everything will be same. Here we will get a minus sign. So omega 1 minus R by 12 plus under root, this thing will remain as it is. So we are getting two values of omega 2 and omega 1, and omega naught is 1 by root LC under root. Okay, omega naught is this value. Add these two values, power dissipation will be half of the maximum. What we want? We want these values very close to omega naught, very close to omega naught. So if you do omega 2 minus omega 1, you will get R by L. You can see this. Okay, I'm not going to do it, but you can see that if you subtract these two values, half and half will become 1, and this part will be cancelled, so r by 12. Also, do if you multiply these two things, if you multiply these two things, 1 by, you will get 1 by LC. Okay, this result right now I am not going to use here, but you will get 1 by root LC, and uh, this will be what, W2 W1 will be omega naught the whole square. Okay, this is also a result. Right now we are not going to use it anywhere, but you can remember it. Okay, now what we want, I will write the quality factor formula, then we will talk about the significance, then I will try to write the definition part is difficult for me. Okay, so I will write definition part later. So quality factor is omega naught by omega 2 minus omega 1. Okay, omega 2 minus omega 1. Now see, if omega 2 and omega 1, so omega 2 and omega 1, they are close to omega naught, this value will be very small and this quality factor will be high. Higher the quality factor, what will happen, our quality of the signal will be, electronic signal will be high. Okay, and lower the quality factor, quality of the signal will be low. I mean, for high quality factor, what will happen, you will hear a clear signal at a particular frequency omega naught, and suddenly if you change the frequency slightly, if you change the frequency slightly, if you increase it and go up to omega 2, power dissipation will be half of the maximum. If you decrease the omega and reach at omega 2, again power dissipation will be half. Okay, now what we are going to do, this is the quality factor, and omega naught is 1 by root LC, and omega 2 minus omega naught is R by L. Omega 2 minus omega 1 is R by L. So quality factor R will be at the bottom and root LC will be like this. Okay, so this is our quality factor. So basically, to have a good quality factor, what we need a smaller resistance, high high sorry, high inductance and low capacitance in a circuit. Okay, now we are going to write another definition. Okay, we already talked about quality factor, but I will also write it again. Higher value of quality factor means very good, very good signal quality, quality quality at resonance, and and it will, and the signal will get diminished quickly, diminished quickly if we increase or decrease the angular frequency from omega naught. Okay, So that is the meaning of quality factor. Now we have other definitions of quality factors. Quality factor. Quality factor is also quality factor is also RMS voltage across inductance or capacitance at resonance. RMS value voltage across the resistance. See, average value is 0, but RMS value is not 0. Now, RMS value across inductance or capacitance. At resonance, what happens? RMS value across the inductance and capacitance, they are same. So what is the difference? Difference is this, that they have opposite sign, they are out of phase. Okay, they have opposite sign, they are out of phase. Okay, basically what is happening, if the inductance is consuming the voltage, if the inductance is consuming the voltage, then capacitance will be providing the voltage. Okay, that kind of situation is that. Okay, so this is omega L IRMS by IRMS into R. Okay, or IRMS 1 by omega C. I will write omega not. Okay, we are talking about resonance. Okay, by IRMS into R. Let us see what we are going to get. IRMS part is gone. Omega naught is 1 by root LC L by R, or IRMS is gone. 1 by R, C is at the bottom. Omega 1 by omega naught will become 1 by root LC. Okay, so in both cases, I believe quality factor is going to be same, right? 1 by R root L by C. So that is the meaning of quality factor. This is